Thank you, David, for the introduction. I will let you know how you should pronounce the name. So it's Pontificia, Universidad Católica de Chile. So it's like like what's the name in English? Pontificia, like from the Pope.
Yeah, don't know.
Yeah,
Exactly.
I don't know. Something like that. Anyways, so let's just start the presentation. If you have any questions, I will be looking at the chat, and also you can raise your hand and I can answer any of your questions. And as David said, today we're going to talk about cut generation procedures via decision diagrams, of course, because this is the Winter School of Decision Diagrams, the best area to do research ever. Okay. So you can see my slide, right? Oh, perfect. I don't know why, but you get a duplicate of my mouse here. I'm sorry for the bug. I wasn't able to figure out how to remove it yesterday when I was practicing. Okay, anyways. Okay, so first I wanted to start with a review of decision diagrams, because since this is a winter school, there's no better way to learn than repetition. So probably this is like the 5th or 6th time that you have seen what a decision diagram is, but I will keep it short, don't worry. So what is a decision diagram? One way to interpret it is to say that it's a graphical encoding of the solution set for a discrete optimization problem. Here I have a little example of an abstract constraint, one of the classic examples. Probably you have seen it many times during the winter school. So what is actually a decision diagram? Well, it's a directed acyclic graph. We have a root node here and a terminal node. We have one layer for each of the decision variables. This is the order decision diagram, actually. And each of the arcs are going to have labels that represent the values of the variable. So here I'm going to use a notation that solid arcs represent, for instance, if we're in the binary case, represent xi equal to 1, and the dash 1 represents xi equal to 0. So this one is x1 equal to 0, and this one x1 equal to 1. And the idea is the following, that if we take any path from the root to the terminal node, we can have a complete variable assignment. So as we can see here in the example, 1, 0, 0, 1 represents this specific path. And we say that we have an exact DB if we have a one-to-one relationship between the paths in the decision diagram and the solutions in our original set X. So in this case, actually, we have an exact DB for this problem. And we say that we have a relaxed DB if we have a superset of the solutions of X. So we're going to have one path for each feasible solution, but some of them are going to be infeasible solutions. But today, what we're going to talk about is cut generation. And we're going to see different ways to do this. So this is the main idea. We have a feasible region that, for instance, can be anything. So for instance, here I draw a circle, a quadratic constraint, and what we want to do is optimize over it. So hopefully what we want to do is actually get the convex pole. So it's like the convex combination of all the integer points. Because if we have this, it's super easy to solve. So what we're going to do is that we're going to transform this feasible region X into a decision diagram. Okay, we're going to model all the integer solutions using a decision diagram. And then we're going to use the decision diagram to generate cuts. So one way to do this is, for instance, a cutting plane algorithm. So we solve, oops, my mouse went away. Okay, so for instance, we solve the continuous relaxation, we get a point, we give this point to the decision diagram. The decision diagram is going to tell us, oh no, it's not part of the convex pole. So we're going to generate a cut that removes it. And then we repeat the procedure over and over again. So we get another point, we give it to a decision diagram, and it gives us another cut. So this is kind of like the main idea of the algorithms that we're going to see. So how we can actually solve a problem using cut generation. And the question is, why do we want to use decision diagrams to generate these cuts instead of other procedures? Well, the main two reasons is that First, we can represent the feasible set of any discrete optimization problem using decision diagrams. So this is super attractive if, for instance, we have nonlinear constraints or some specific structures that are better represented with decision diagrams instead of classic techniques. And also, one of the nice things that we have also seen during this winter school is the network flow model of the decision diagram. This gives us basically a linear representation of all the solutions of the decision diagram. So we're actually going to use this a lot for generating our cuts. But the question then is, well, why don't we just use this model directly instead of just generating cuts? And the reason is because this DD network flow might be too large to actually just put it in your MIP model and, I don't know, let Cplex or Google resolve it. So what we're going to do instead is add cut little by little, because usually what happens is that you need a small set of constraints to actually solve your problem. So this procedure, it could be much more efficient in practice. So just to give a brief overview of what we're going to see today, we're going to review this network flow model and a little bit of polyhedral theory, because it's kind of like the main foundation for all our techniques. Then what we're going to do is review some of the DD cuts in the literature, starting from the oldest to the newest ones, the subgradient cuts, target cuts, and then combinatorial flow cuts. Then we're going to see some enhancement, how we can improve these cuts using also decision diagrams. We have some computational comparison between all of these techniques, and summary conclusions and some open questions. And of course, since this is my talk, I will focus mostly on my work, but I will briefly review the other techniques so we can get a general idea of the different ways that we can generate cuts using decision diagrams. Okay, so let's start with the network flow formulation. I'm pretty sure you have seen this before, but as I said, there's no better word to learn than repetition, right? So this is what we're going to have, a feasible set X, and is integer values. We're going to assume that we have an exact DD for this feasible X, and here's some notation. We use A in and A out to represent incoming and outgoing arcs for a specific node in the DD. B is the value associated to arc or its label, depending on how you want to call it. And the model has two variables, basically. We have the flow passing from each arc on the decision diagram, and we have the regional variables that define the set X. So the network flow model, we can see it as follows. Basically, the first constraint tells us the balance of flow. So whatever comes into a node, it should go out to a node. The other constraints that we impose that the flow has to be equal to 1, passing throughout the whole decision diagram. And then we have the constraints that relate the flow with the original variable. So basically tell us that the next point is a convex combination of all the paths passing through the diagram. This is what more or less is saying constraint 1C. And there are two ways to see this model. First is if we assume that y are integer, actually what this will give us is the path specifically for the decision diagram. But in this case, what we actually want is when y is continuous, because we actually want the convex combination of all the solutions that are representing the decision diagram. This is how we're going to use them. And the nice thing and the main property and why everything works is the following result, that this formulation represents the convex whole of X. So basically what this equation here says is that if we have this network flow model and we project it only on the X variable, we get back the convex whole of our original set. And this was proven in 2007 for the binary case, and then quite recently extended actually for when we have MDDs or decision diagrams with the integer values. And why is it good? Well, as I said before, if we have the convex whole, we can solve the problem using just linear programming. So we don't need to do any branching or any type of search. We can just give it to a linear programming solver and it will give us the solution. And also, since I said, as I said before, this model can be very large because it depends on the size of the decision diagram, the number of variables will depend on the number of parts, the constraints on the number of nodes. So what we're going to do is that actually, if this is too large, we can add paths that define this convex hull little by little while we solve our problem. Okay, so now let's see how we can actually use this technique to generate planes in a cutting plane type of algorithm. So the first one that I'm going to review is what I'm going to call subgradient cuts. First of all, let's review a little bit of what do we mean with separating a point. So what we're going to have is, for instance, a point x prime that is not inside the convex hull. We only care about the ones that are inside. We can separate this point if we find some parameters lambda and lambda 0, such that the constraint is going to be valid for all the points in X, but it's going to leave outside the point that we want to separate, that is X prime. So the nice thing is that we can basically reformulate the same idea, but now with the decision diagram. So this is what I call the D separation. So we say that X prime is not in the convex hull of X if there exists, again, a lambda such that the constraint that I get is will remove the point that that is outside, that is X prime. And since here we have a decision diagram, what we can do is that this lambda 0 coefficient, it could be just the maximum value for all the x's that are inside the decision diagram. So here is all the solutions that are inside the decision diagram. Here is the convex hull. So it's basically the network flow model that we had before. If we optimize it using this parameter lambda, we set this lambda 0 and we will get the cut that we want that is feasible, but it will remove the point that we want to separate. And the question is now, how do we find this lambda, specifically if we have a decision diagram? And the good thing is that it's quite simple. We just need to use an iterative subgradient procedure. This is just the main idea. Basically, what we do is that we choose an arbitrary any lambda that we want, an initial point. Then what we're going to do is that we solve this maximization problem. They look very intimidating because we're saying like X in the convex hull of the decision diagram, blah, blah, blah. But actually, the only thing that we need to solve here is a longest path over the decision diagram. So we basically, a longest path where the coefficients are whatever the lambda that we choose at the beginning. And then what we do is that we see the constraint that it gets us with the lambda 0. If it works, great. And if it doesn't work and we need to update it, what we do is some subgradient routine to update our lambda. And then we start from the beginning again with the new lambda. And so the longest path and so on and so forth until we converge to the cut that will separate X prime. So the main takeaway here is that in the end, the only thing that we need to do to find this cut is solve longest path problems over the DD. And this can be done in polynomial time over the size of the decision diagram. So in practice, it's very fast and very efficient. So some advantages of the procedure, as I said, well, we need to only solve a longest path problem over the DD, which is quite easy. And if we want to take it to extreme and converge to the optimal lambda, what we're going to get is a cut that maximizes the violation distance. So this expression here. So it's going to be actually quite strong. It's going to be touching the convex hull, so it's going to be a phase. So it has some desirable properties. But there are some disadvantages of this procedure. One is that since it's an iterative procedure, it might take several iterations to converge. And it has some conversion issues because what happens is that sometimes you can go into, basically you have like an unbounded problem, so you can go to the infinity. But luckily for us, Daniel and William work on this, and they show that basically you need some normalization constraints or add a projection step in your subgradient, and then you can converge, and it's quite stable. So it's kind of like a small issue, but you can address it quite simply. But the main problem about this technique is that in theory is great, but in practice, and we will see it when I show you some results, is that it's usually hard to find cuts for points that are too close to the convex hull. This iterative procedure has some issues converging, and sometimes it's very hard to separate points that are too close to your convex hull. So, okay, this was the first procedure. Let's go to the second one. And here is the work on target cuts. I'm going to explain very briefly the main intuition. So we have our set X, the convex hull, and we have our X prime that we want to separate. So what you do is that you choose a point inside the convex hull, W, and you take an array that goes from that point to the point that you want to separate. And this arrow basically tell us what is the phase, is the constraint that is defining the convex hull that will separate that cut, and it returns it. So basically give us the strongest possible cuts that we can get. And the main issue, I mean, this idea doesn't have anything to do with decision diagrams. And what you need to do to actually get these cuts is what is called a polar set of set X. And I'm going to go into the details, but let's just say that it's usually very hard to define, and that's why it's not very used in practice. But the nice thing that Christian and William proved in their paper is that actually you can get this polar set using the decision diagrams. So this is where the network flow models comes and saves the day, because basically, I was said before, the network flow model can give us the convex hull, but if we take the dual, it also can give us the polar set. And this is the main component to get these cuts. So what they did, just a brief summary, is that you can get what is called a cut generation linear program. So it's basically a linear program where you have this network flow model of the decision diagram to generate these cuts. And it's basically as efficient as solving the network flow model of the decision diagram. It has some extra constraints, but it's almost the same as solving this network flow. So in terms of advantages, these are, in terms of theory, these are the strongest cuts that you can get, are called what we say facet defining. So there's no better cut that you can get using any other techniques. But it has some disadvantages. First, the optimization probably is unbounded. This is not a big disadvantage, it's just that you need some extra work handling the special case when you get, instead of a solution of your LP, extreme point, you get an array, you have to do an extra step, but it's just a little bit of extra implementation, nothing too much to worry about. But the main issue is that in practice, and we will see it with the results, is that it can be computationally expensive, because again, you have to solve an LP to find the cut, which is in general not expensive, but you will have to do this many times. And these LPs have usually are very large because they are proportional to the size of the decision diagram of their network flow model. So it depends on the number of nodes or arcs that you have. So if you have a large DD, solving this LP to generate only one cut, it can take quite some time. So then, now we're going to go to what I call the combinatorial flow cuts. These are the works that I work with Andre and Chris. They was published very recently. And here, what we're going to do is that we're going to focus only in the binary case. So we're going to be talking about BDDs, binary decision diagrams, instead of the other ones that were more general, that are for any type of discrete program. And in what follows, what we're going to show you is first a novel network flow polytope. So this network flow model that we have before, we're going to change it a little bit for this binary case. And we're going to we propose two different ways to generate cuts using this new network flow model. One procedure is complete. You can remove any fractional point that you want, but again, you have to solve an LP. And the other one is incomplete. It might not remove all the points that you want, but it's very computationally efficient. So let's go to the first one. That is let's see this new network flow model that we have. So this is the original network flow model. We have our balance of flow equality. We said that the flow has to be equal to 1, and then we have this convex combination basically of the arcs and x. Since here we're talking about binary variables, what happens is that this expression only considers the arcs that have a label or a value equal to 1. We don't consider the ones on 0 because 0 times a variable is just 0. So what we presuppose is this new network flow model. So it has the two first constraints are the same, balance of flow, flow equal to 1, but we express this combination differently, and we express it as the capacity of the arcs. So what we say is that all the arcs in the same layer that have an arc that has value equal to 1, they're going to be constrained to have flow no more than xi. And in another layer I, where all the arcs have a value equal to 0, they're going to have a limited capacity of 1 minus xi. Okay? And the nice thing about this model, so yeah, as I said here, like basically we transform this constraint into these two constraints. The nice thing about this model first is that it's bounded, which is a little bit better. We don't have to worry about unboundedness that we have in the other procedures. And also we can show that these two models are actually equivalent. They have the same number of solutions, so we only need to do the, so it doesn't matter which one you choose, it's a matter of preference and the structure that everyone has. And since they are equivalent, we also have that if we project over the original variables, the x variables, we get the convex whole again. So we're basically not losing anything. We added more, a little bit more constraints, but we have some additional properties. And this is going to be the main source for our cuts. So the first cut are what I call the general BDD flow cuts. So the main idea is that we want to solve a max flow problem over this network flow model that we have. So the problem is very simple. It's basically the same constraints that we had before, but we remove the constraint that said that the flow had to be equal to 1. And instead of having that constraint, we say that we want to maximize the flow. And what we can show actually is that if we solve this problem, this max flow problem, we can identify if a point is inside the convex hole or not. So if the flow is equal to 1, we're inside, and vice versa. If the point is inside the convex hole, the flow has to be equal to 1. If it's different to 1, we know that it's outside, so we can remove it. And to remove it, what we do, here again, I'm being very general. What we do is that we get the dual solution of this problem. We generate this is the form of the cut that we get using these Greek variables that are the dual solutions. And the nice thing is that we were able to show that this type of inequalities define the whole convex hole of X. So basically our cuts will define the convex hole, so they're going to be quite strong. So in terms of advantages, as I said, the cut generation linear program is bounded, so we don't have to have any special case or implementation details for unbound solutions. And we can separate any integer or fractional points inside the convex hole. But we have some disadvantages. First is that it's only applicable to the binary sets. We haven't extended for the general integer problems. And it can be a little bit computationally expensive. This is the same as with the target cuts. We have to solve an LP that is grows proportionally to the size of the DD. So the bigger your DD, the harder it's going to get to be to separate points and generate these cuts. So that motivates us to do, well, can we do something a little bit more efficient? And here is what we call our combinatorial BDD flow cut. So what we're going to do is we're going to generate another network flow polytope. There is a relaxation of our original one. What we do here is that before we have a constraint that was the capacity of the arcs, well, it was like, for all the arcs, this is my capacity, like joint capacity. So here what we do is that we have a capacity, but for each arc individually. And the nice thing about if we have this structure is that then when we want to optimize to generate the cuts, this is a classic max flow problem, like textbook max flow problem over a decision diagram over our BBB. So the nice thing is that there are a lot of algorithms that were to solve max flow problems without having to build a LLP. So we can use any of the textbook max flow algorithms to solve this. And actually, to compute our cut, we take advantage of also this max flow min cut duality to generate our cuts. But the only drawback is that since this new polytope is a relaxation of the older one, it might not cut all of the fractional solutions. So that's why we say that this technique is incomplete. It might cut it, it might not cut it, but in general, it works pretty well, actually. And here I have a small example of how it works. So we have an infeasible point that is the following. These values are going to be the capacities of my arc. So if the arc has value 1, it's solid, the capacity is 0.7, that is the value of x1. If it's not, it's 1 minus x1, so 0.3. So these are the capacities. What we do is that we solve the max flow min cut problem. So here it's easier to see the min cut. So how I can cut the flow here with the minimum value, that would be selecting this arc here and here, give me a value 0.4. Since it's not equal to 1, we know that this value is infeasible, and then we just generate our cut. As I said before, it's just the dual solutions to generate the cut. And actually here we get a very simple cut that is x1 plus x2 less or equal to 1. And if I don't misrecall, this is actually a really strong cut for this problem. It's facet defined, the best that you can get. So even if the technique is not, it doesn't have like nice theoretical guarantees, you can still get a lot from it. Okay, so let's see again, advantages and disadvantages. Well, we can separate, the next thing is that we can separate all the integer points outside of the convex hull of X, even though we cannot separate all of the fractional ones. And is extremely fast. I would say from all the techniques, and I will show you with some results, is the fastest one there. Because we just need to solve a max flow or a min cut problem over the VDD, and there are a lot of algorithms that we can use. And at least in my implementation, I just use a standard algorithms from textbooks, and it works. Disadvantages, again, this is just for binary sets. So we haven't extended yet to integer sets. And also, as I said, this is an incomplete procedure, so it might not cut off all your infeasible fractional points. But in practice, it works pretty well. So I don't know if there's any questions so far before I move to the next topic. Okay. So let's move on. Yeah, so now I'm going to show you again part of our work where we, I call it like enhancement technique, but basically how to improve cuts that we get either from a decision diagram or from other techniques using a VDD to make them stronger. And here again, we're going to focus on the binary case. So we propose what we call a combinatorial lifting procedure based on VDD. So the main idea here, again, is related to the convex hull. What we want to do, we want to create valid inequalities that touch as many points on the convex hull as possible. So in the drawing before, hopefully something that actually defined a little triangle that I had before. And in terms of the theoretical assumption for the results that follow, we assume that we have a VDD that exactly represents X. Okay. So we have basically two steps. The first one is that if we get any constraint, we can use the VDD to make sure that at least it touch our convex hull. So that's called a phase. So at least we have a phase. And this is something that already existed and it's very simple. I will explain that later. But the main contribution is this other part. It's like we have our constraint and we're going to do is tilt it or rotate it a little bit. I will show you how it looks in a few slides. To increase its dimension. So it means that we're touching more points, so the cut that we get is stronger. And we can repeat the step 2 multiple times until we cannot do it anymore. And yeah, here are all the assumptions, and also for the cuts in general, we were assuming that we have an exact DD, but actually in practice, what you do is that you build the VDD as big as you can. It could be exact or it could be a relaxed one, and then you generate this cut, and everything will remain valid. It's just that it's not going to be as strong as if you had the exact VDD. Okay, so let's look at this strengthening part. So we have our value inequality. What we're going to do, again, compute the longest path, because it's like the most popular algorithm that you do with VDDs. You're always computing longest paths. You cannot get rid of it, right? So we compute the longest path on the VDD, where the values of the arc, the lengths of the arcs are going to be the value of the arc times the coefficient of the constraint that we have here. And then what we do to strengthen the cut, this is very simple. It's just that this pi 0 is going to be actually the value of this longest path. So that will guarantee us that we're actually touching the convex hull. We get a phase of the convex hull. So this procedure is very general, it's nothing new, and it can be done both for VDDs or MVDs, discrete or binary values. So, oops. Okay, so here I have a small example. So this is the pi that we have, the values, the coefficients of the constraint. This will be the length of the arcs for our longest path problem. We compute the longest path that is actually this value here that has a length of 2. So then the constraint that we get is basically combining these coefficients and then putting less than or equal to 2. And the nice thing here we can see, and this is going to be important, that actually the longest path that here actually there are two paths that get value of 2. These 2 paths represent 2 points that are actually going to be part of the phase of the constraint that we get. So we're going to use this a lot for our theoretical results. So now let's go to the second part. That is, okay, I have my constraint that's actually touching my convex hull, as I said here. So it's touching, for instance, in point, but we want to rotate it, tilt it to get something stronger. So, sorry. So hopefully we can get something like this. That is now touching 2 points, so it's much stronger than having the value here. And to do this, what we're going to use is 0-1 disjunctions. A value that we are going to call D slack or disjunctive slack to change the coefficients of our constraint to do this rotation. So this D slack we define it as follows. We have the coefficients of our constraint, and now what we're going to do is that we're going to optimize the problem when one of the variables is equal to 0 and one of the variables is equal to 1, and we take the difference. So that's why we get this 0-1 disjunction, and this difference is what we call the D slack. And our procedure is as follows. It says that if this one of these coefficients, I can choose any variable. If one of these ones is different to 0, then I can get a new constraint by just changing some of the coefficients with this lambda, with this difference, with this D slack, as follows. And I'm going to go too much on the details. But the nice thing is that first, it has a strong relationship with a lot of other techniques that existed before, especially on the disjunctive programming literature. But also it has some really strong theoretical properties. So for instance, we can say that this new constraint that we have, first of all, is valid. So we're not adding anything that is going to remove points that we actually want in our problem. The induced phase, the constraint that we get intersected with the convex code has higher dimensions. So that means that basically that is stronger. And also that it will actually remove more fractional points that we had before. So it basically has all the nice properties that we want. We actually get something stronger every time we do this procedure. So the problem is that there are some drawbacks. In theory, what we want is to get the strongest constraint, that is the facet defining. But we were able to show with some examples that we might not get facet defining inequalities, because what happens is that our procedure only works when these lambdas are positive. So facet defining would mean that all these lambdas are 0, but not because all these lambdas are 0 are going to have a facet defining inequality. And since our procedure needs some lambda that is different to 0, it might stop before it actually should. And it's also very sensitive to the starting inequality and how I do this rotation, this lifting, which coefficient I use to change the coefficients of my constraint. But there are also some special cases where this works perfectly, again, relying on works that were before in the literature. We have some special cases where it works very well, for instance, for monotonic sets. That could be, for instance, an abstract problem. And also we were able to show that under certain conditions, if we do this lifting in a specific case, a specific order, we actually get facet defining inequalities. So here I have just a small example of how we actually compute all of these with the decision diagrams. Because so far I haven't mentioned decision diagrams on this lifting. I'm just saying, like, you need to solve these two problems, but they are as hard as the original problem. They're just fixing one variable. But the nice thing is that if you have a decision diagram for my set X, I can do this very efficiently, again, just computing longest path. So what we do is that we compute the longest path from the root to any node and the terminal to every node. This can be just efficiently done in one pass. I mean, two passes, from top to bottom and bottom to top. And basically this problem where we fix xi equal to 0 is the same as in all the arcs in one layer. So all the arcs from U to U prime that are in the same layer that have a value equal to 0, and we choose the maximum value of those. And the same is for xi equal to 1. So here I have a small example for this. We have, for instance, the original constraint with pi as follows. We compute the longest path everywhere. And something happened. Okay. So what I'm going to do is, for instance, trying to compute this lambda 3, the disjunction for the third variable. So I compute the shortest path from R to node 3, node 4, and from T to node 5. I do all the differences of the arcs, basically compute this value here, and I get that my lambda 3 should be 1. That is the maximum if all my arcs have value 0. So it will be, like for instance, this case 1 and then 0, 0, and 2 if my arcs have value 1. So the d slack would be -1, so we can rotate the inequality. Here I have a small example of how it works, like the whole procedure. We have our original inequality that is already touching the convex code, so we compute the longest path all over. Here I'm just showing the lengths of the arcs for the longest path procedure. We compute all the lambdas. We can do this, as I said, like 2 passes over decision diagrams, and we get all of them. And I choose, here we have 3 values different to 0, but I just choose the second one, just because. So now the new constraint is basically this coefficient here that was 1. I have to subtract -1, so I get a 0. So this is the new constraint, and I repeat the whole thing again. longest path with the new coefficients. I get my disjunctive slats. I choose any one of them that is different to 0, and I update my constraints. And now I get x1 plus x3 less than or equal to 1. And now I do the whole thing again, compute the longest path. And now we can see that all the disjunctive slats are equal to 0, so I cannot rotate and we stay there. And in this case, the resulting inequality is fast defined. So it's the strongest that you can get, that it will remove any point that the original constraint was removed. Okay, so now we have seen a lot of theory and a lot of techniques. So let's see how all compare to each other to see what you should do in practice. Our application, this is from our paper. We focus on second-order cones that are usually quite challenging for commercial solvers, even though simplex and Gurobi can solve these problems. They are not that efficient doing so. What we do is that basically we have a linear constraint, a lot of the second-order cone constraints. What we do is that we're going to have one BD for each constraint. And since usually these problems were quite large, we actually have a relaxed limit. We have at most 4,000 nodes per layer. And this is our setup. We have all in all 270 instances, 1 hour time limit, and we only added cuts at the root node. And basically we compare everything. We compare Cplex using full power of Cplex, and then all the cuts that I mentioned. So here B proj is the subgrading cuts with this additional step of the projection to make it more stable. We have the target cuts, the general flow cuts, and these combinatorial cuts again. I will be reminding you what were each of these when we see the results. And I use this plus L that it says that it uses our lifting procedure to improve the cuts that we get, and plus NL, so no lifting. Okay, so these are the overall results. What I'm showing here in the first side of the graph, we have the time and the number of instances solved. So the more time they have, more instances solved to optimality. And we have all the different procedures. And then on the second side of the graph, the right-hand side, what we have is that for the instances that weren't able to solve on our time limit, we have the accumulated gap that they have. So how many instances have, I don't know, gap equal to 1, gap equal to 2, so on, until gap equal to 20, blah, blah, gap equal to 14, and so on. So let's see how the techniques are. So the bigger the lines here, the more up they are, and the better the techniques. And what techniques we have here? We have, well, all the ones that were solving linear programs. We have the target cuts and the general flow cuts. And here the dashed ones represent that they don't have any lifting procedure, and the ones with the lifting are solid. And for the target cuts, since they didn't need any lifting, they were already as strong as they can get. We actually, what we did is combine this. We did some flow cuts first, and then when we did these ones stopped, we started using target cuts. All in all, they're all more or less here. There are all these like complete procedures that are guaranteed to give us in the end the best cuts possible. Then the other line that we have here is this cyan line that is the flow cuts. So these were the incomplete ones. It doesn't guarantee us to cut everything, but if we enhance it with the lifting, they were performing quite well. They were actually surpassing Cplex, that is this dark blue line. And then down below here with Cplex, we have the subgradient cuts with this projection step plus the lifting. As I said, what happened is that usually they cut that much, like they added cut at the beginning, but then if they were too close to a convex fault, they were struggling to converge. So that's why they weren't performing that well. And also the BD flow cuts without the lifting, again, they weren't adding too many cuts, they weren't too strong. So they were similar to just using Cplex without any of these enhancements. So let's look a little bit more detailed results. So All in all, we have root information, root gap, time at the root node, number of cuts that we add. And the main thing that I wanted to show here is the value of having this lifting procedure. So first, if we look at the flow cuts or the subgradient cuts, the projection ones, we see that there was an improvement on the root gap with the lifting. For the general cuts, it wasn't because, yeah, it was adding better cuts, but in the end, it would converge to the same root gap. And for the target cuts, we didn't need the lifting. But it's nice to see, for instance, that the time and the root is significantly decreased, especially for the general cuts, because since we enhanced that with the lifting, here what we had is that the cuts were stronger, so we needed to add less cut, so we spent less time in the movement. And we can see also here that we were adding less cuts. The same for the projection cuts and also for the flow ones. And the other thing I want to show, and this is quite interesting, is how much time each of these techniques takes to separate one solution. So here I just average how much time it takes to separate one feasible point. And we can see these flow cuts that these were the ones that we just solved a max flow problem, a standard one from a textbook over a direct acyclic graph. It takes 0.01 seconds, 2 orders of magnitude faster than solving, for instance, the general cuts or the target one cuts that we needed to solve an LP. So that's why I wanted to actually this time matters a lot. And that's why, for instance, the root time here for the general cuts or the target ones is much higher than the other things. Not only they're adding more cuts, but also they're 20 times, 100 times slower. Okay. So we wanted to see a little, like, take these two techniques to the extremes. So we have the most efficient ones, the ones that with the best theoretical guarantee. So the flow ones, if we add them to the root node, the number of instances that they were able to solve, it wasn't too much, 149, very slow, very small. But if we now add the cuts in every single node during search, like be very extreme about it, we were able to solve 177 instances, so almost 30 more. But the opposite for the target cuts. The target cuts were very good if we only add a few of them because they were more computationally expensive. So at the root node, we were solving 172 instances. But if we add them in every single node of the search, since they were taking 100 times more time, in the end we solved less instances, like barely 100. And we can see the same way, like solving times and everything for the instances that everybody was able to solve. So then we say, well, what if we combine them? Let's take the best of the two worlds. We propose this hybrid approach. So basically we take the target cuts at the root node because they were performing very well there. So we get the strongest cuts that we get at the beginning of the search. And these BDD flow cuts plus or lifting, that was very cheap, we add them during search. Here we actually get the best results. We solved 179 instances, so it was the best over all the combinations and all the techniques that we tried. Also, the runtimes were smaller, the gap, the number of nodes, and we added a bunch of cuts, but most of them were during search. So all in all, this is kind of like, I would say, the state of the art of all the cut generation technique with decision diagrams. So now, just to conclude, I want to give a brief summary of what we saw. We have the advantages. We saw advantages of using decision diagrams to generate cuts. Basically, they can represent hard constraints. And since these nice properties of the network flow models, we're guaranteed to get a good theoretical guarantees of the cuts that we generate. And there are different ways to generate the cuts. We saw 4 different ways here, but as I said, there's no clear winner. And combining them, it looks like it's the best alternative. Yeah, and in terms of open questions, one of the things that kind of like is bugging my mind and I find interesting is that can we get the best of the two worlds? I mean, like, can we get faster defining inequalities, the best and the strongest that we can get using decision diagrams, but without the overhead of the solving an LP model? And we get like something efficient and also very strong cuts. And how I see this kind of like idea is basically we were talking in the first day, the constraint we can see it as an implicit model. An explicit model will be the DD, and then we generating the cuts, we get again an implicit model, but hopefully something stronger. So my question goes like, how we get this from IP to DD to IoT, but as efficient as possible and with the strongest cuts as possible. So thank you so much. If there's any question, I will be happy to answer.
Thank you. Virtual applause, of course. Yeah, look, we have a question. Franklin, you can either put it in the chat or feel free to say it orally, up to you.
Okay. Hi, thank you for the brilliant presentation. It was really nice. My question concerns have you ever thought of comparing I want to understand how these cuts can compare with traditionally known cuts that for some problems. For example, if you take the knapsack problem, there are cuts that are known like cover inequalities and lifted cover inequalities. How do these cuts can compare to those type of traditionally known cuts? So one example was on your slide 26, where you had.
Yes, continue. 26.
Yes, on slide 26, I just want, yeah, here we have a starting inequalities with 0.5, x1, x2, x3 less than equal to 2. So just looking at the inequalities, you can have like the cover inequalities with a coefficient of 1 instead of 0.5 for x1, which is stronger than this one. I understand that later on, it can be strengthened to get something much interesting, but instead of comparing with Cplex, did you think of comparing with those kind of traditionally known inequalities?
Yeah, no, thank you for your question. Actually, something that we did. Yeah, so for this specific example, since we didn't test it on knapsack, we didn't compare it. But as you can see, like for instance here, the inequality that we get is actually a cover cut. So there's like a lot of relationship in that sense. And also we rely a lot of the theory of the knapsack to prove some of the guarantees for the lifting. In terms of the results, actually, as I said, we tested on the second order cone cut, but I don't have the results here, but in our paper, what we also did is to compare to the problem that is called the second order knapsack cone. And there were a lot of cuts in the literature for this type of problem, very similar to the knapsack type of inequalities, cover cut, extended cover cuts, and so on. And we actually compared to those techniques in our paper. I'm sorry, I don't have the results here. And they were, all the VDD cuts, if I don't misrecall, were doing much better than the cuts, specifically defined for these problems in the literature.
Okay, thank you.
Awesome. Great. Any other questions from the group? Yes, go ahead, Willem.
Morning. Thank you for really a very nice presentation and I think very good work. I wanted to follow up on the previous question. Did you test this procedure on integer programming, pure integer linear programming problems? And what's the effect there? Because there's relatively cheap ways to get relatively strong cuts in that area. And then we did, of course, some experiments as well in our work on a similar topic. And it was difficult to find, say, MIPLib instances at which it was doing well. So, I mean, it was doing fine, but it was not really outperforming existing methods. Did you experiment with MIPLib or similar IP formulations?
Yeah, no, thank you for the question. Very good question. In our case, no, we didn't want to compare to using the MIPLib to ILP problems, especially because of that. Like there's so much literature there, the procedures are so strong that it's hard to find something that will actually outperform. So that's why we wanted to go to the second order cone literature, that there was some work there, but still a lot more room for improvement. So kind of like that was our strategy. So no, I haven't tried this here because it looked like it was already overcrowded and it was hard to actually show the value of the techniques there.
Thanks.
Great. Other questions? Okay, if not, then let's thank the speaker again. Very good work. Yeah, happy to see future work that you're able to progress in on this area. Great. So I think we have a break here. You can hang out and have a conversation with people if you'd like. But we will start up again at 11:15. Great work, Margarita. Merv, how are you? I haven't seen you in a very long time.
Yes, hi Dave. Good to see you.
How's Toronto?
I haven't been here in the past 1.5 months, but I'm back now, just a couple days ago. It seems like winter is here already. There's snow, surprisingly. So yeah.
Happens quickly, huh?
Yeah. Hasn't been too bad. I mean, we are in December, no?
Yeah. Cool.
How are things with you?
Good. Busy as usual. I'm happy the semester's winding down. I'm teaching 2 classes right now, so it's a good going to be very excited to have a little break from that. For sure.
Almost there. There.
Cool. All right, so we'll take a break, and you're next, right? If I'm not mistaken.